So let me introduce our next speaker. Thank you. Yeah, Elliott Rouse is an assistant professor at the University of Michigan, and he's really a pioneer in like wearable robots, in particular robotic prosthesis. His research has been covered by multiple media, including TED Talk and CNN Discovery Channel. Elliott, can you share your screen? Yeah, please take a wait. Thank you.
So it was just holding my desktop. Let me try that again.
Yeah. We have time. Yeah, all right.
There we go. All right, can you see my screen?
Yeah.
Okay, thank you, and thanks especially to Ham and the other organizers. This is such a fantastic workshop. Today I'm going to tell you a little bit about a project that's going on in our research group, the development of an open source robotic leg. Before we get started, I'd like to tell you a little bit about my research group, the Neurobionics Lab, where first and foremost, we study basic biomechanical science. And what I mean by that is we study how the nervous system regulates joint mechanics or joint mechanical impedance during locomotion. And we also study perception and psychophysics and kind of preference-based design and control. And we also develop wearable robotic systems like the open source leg that I'll talk about today. We have kind of a host of other technologies that I won't have time to discuss. But what I think is kind of unique about our approach is that we pursue these processes in parallel and they feed back on each other. So the basic science that we're doing informs wearable robots that we build. We also leverage our wearable robots to answer fundamental science questions. So let's talk a little bit about the open source robotic leg. So what's motivated this project is that control is really one of the greatest barriers preventing the widespread clinical impact of robotic legs. Fortunately, we have many talented researchers around the country and around the world studying the control of robotic legs. But before they can test their control strategy, they have to develop a robotic leg on which to test. And this is problematic for two reasons. Firstly, it hinders comparison between the different control strategies because it's difficult to decouple the results that stem from the hardware from the control strategy. And if you look at the prostheses on the screen, you can tell they have vastly different properties. And the second issue is that it's incredibly inefficient for our field. To develop a robotic leg, it costs hundreds of thousands of dollars in many years, and we're doing this over and over again. So we try to come up with a solution to this, and our idea is to come up with an open source robotic leg. It was redesigned from the ground up, and the idea is that it's easy to manufacture, assemble, and control. The system is modular, so it can be used with a knee or ankle together or separately. If we look under the hood, I want to kind of point out a few features. One feature that we've heard consistently today is we use motors that were developed by the drone industry, and the high torque density from these motors really opens some doors in terms of design. Our transmission ratio for this leg is about 3 to 6 times lower than what would be conventionally used, about 50 to 1. This let us use belt drive transmissions, which we use because they're quiet, efficient, and low cost. They also don't have the high price tags and long lead times associated with precision machine components. We've also integrated different sensing modalities that lets researchers kind of customize the sensor set for their particular approach. It includes an embedded 6-axis load cell that can be placed in the knee or ankle. There's IMUs on each degree of freedom, joint angle encoders, motor current and voltage information, so sort of a host of sensing information available. And the system is fully contained, so it contains onboard battery and control embedded systems. And the idea is to encourage researchers to test outside the lab, which I think is another kind of key limitation that we need to move through as a field. In the knee joint, we've heard a few times about series elastic actuators, and we designed kind of a design novelty in the knee that I'd like to talk about for just a second. So series elastic actuators, I think everyone here is probably familiar with them, but they were developed in the kind of mid to late 90s, and the idea is to place an elastic element kind of between the output of the transmission and the load. And this has many benefits. It enables improved torque sensing and torque fidelity, better energy storage and return, and shock tolerance. And these are things that are especially important in wearable robotic systems. But it also comes with some challenges. It reduces force or torque bandwidth and adds significant complexity and mass. And these are things that people don't want in wearable robotic systems. So we wanted to design a system that could be used by both groups. To that end, we developed a novel type of torsion spring that I'm going to talk about for a minute. It's compact and high displacement. The spring fits around the axis of the knee joint. So if we kind of look inside, we see something that looks like this. The spring is 24 individual radially spaced cantilever beams, and it's a disc. It's about 4 millimeters thick. And what we do is we tailored those cantilever beams to connect with the involute profile of a gear that slides through the center of the disc using rolling contact. To give you a little bit of an idea of what it's like to interact with one of these springs, here's kind of me pushing on one of my desks. And if you look closely, you can see as I push on it, it rotates that gear and it deflects those individual cantilevers. So this gave us this kind of really compact, high displacement torsion spring. The spring disc can be included within the design up to about 6 discs. So the idea was people can not only select whether the system is series elastic or rigid, but they can also select the specific elasticity within certain bounds. And if we look about how we implemented it into the design, we'll look at a cutaway of the knee, and we're going to look inside the last stage of the timing belt system. So if we open up that timing belt pulley, we can see that the springs kind of fit inside there upon assembly, and sort of up to 6 of them. That's kind of limited at a deflection of about 15 degrees. So this let us implement the series elastic mechanism for very little added mass and essentially no added volume. I want to tell you a little bit about our design process. I can only go through it quickly, but if you're interested in more details, the publication is referenced at the bottom of the screen. And we begin by defining the output requirements. So what does it have to do? We take a subject's mass, we estimate something like 90 to 100 kilograms, and we use biomechanical data from the literature to estimate the output kinetics and kinematics. We then translate that information to kind of a second step, and we translate to the motor kind of torque and velocity information that's required using the transmission ratio, transmission efficiency, and any series elastic components. Once we know the kind of motor torque and speed information using the kind of electromechanical model of brushless motors, we can convert that to the required current and voltage. And we use kind of the Q-axis current and voltage as kind of a DC representation. And this helps us understand the voltage needed from the power supply and also to appropriately spec the brushless motor driver. And we use the Q-axis current coupled with the phase resistance to estimate the increase in winding temperature. And to do that, we need thermal resistances and thermal capacitances of the motor. And those are not available for most drone motors, certainly not in realistic testing conditions without forced convection. We've actually estimated those parameters ourselves. Here's an example of a test that we ran where we run 8 amps through 2 leads of the brushless motor. And we look at how the temperature increases, and we use this information to model the resistance capacitances. We convert that 8 amps between 2 leads into the equivalent Q-axis thermal power and then the equivalent Q-axis current. And if you look at that picture, if you know what you're looking at on the left-hand side, you can see that there's kind of an interesting thermal pattern. And that kind of confirmed to us that the motor was delta wound, which is also important for our modeling. One of the final steps is that we also, once we're done kind of speccing the motor and transmission, is we do the physical designs. We do the layouts, the structural support, and we try to minimize kind of mass and volume. And then our last step is that this kind of repeats, and there's an iteration process that goes on where we're investigating different transmission ratios, different motors, and different physical layouts. And this process is kind of what we used to design our open source robotic leg. I wanted to take just a minute and contrast what I think is a more conventional approach with the approach that we've kind of landed on in my research group. The typical approach, as we've heard, is kind of to fail often and early and kind of iterate with many prototype versions. And this is very promising, and I'm a big fan of that approach. But as we've kind of been developing systems over the past 5 or 6 years, something that I've noticed is that our approach is a little bit different. The systems that we designed, in my mind, are actually like relatively simple systems. So we're not doing some of the complexity or leading edge mechanism or actuator work that we've seen today. Our systems are relatively simple. So we've developed this kind of 5-step design process, which lets us spend a little bit more time up front doing the analysis and physical layout design. And then when we prototype something, it's a little bit more relatively refined. And that has worked for us. I think there's kind of strengths and weaknesses, but I just wanted to highlight that in the kind of the context of this workshop. The next, I'd like to highlight some of the control performance that we've done on testing the open source robotic leg, kind of first under position control. So here you're seeing the knee and the ankle do step response tests in the time domain at a few different amplitudes. And if we look at those plots, we're looking at tests of 5, 10, and kind of 15 degrees. And you can see it performs very well. We've also estimated the frequency response, which is kind of a cooler looking test, where the knee and the ankle just shakes around kind of as hard as it can following a band limited white noise signal. And then we use frequency domain based system identification to estimate the Bode plot. And it looks something like this. And we also varied the amplitude of the band limited white noise signal. And the kind of takeaways for the position controller, the rise time is about 26 milliseconds and the bandwidth is about 10 to 20 hertz, which is sufficient for wearable robotics use in many cases. It's about 3 to 5 times higher than the human body. If we look at our current control, let's see if I can get the slide to change. There we go. We did some current control tests as well. So here we're using current as a proxy for torque. We're looking at Q-axis step responses here up to about 3 to 3.5 amps. We did a similar test where we tested the bandwidth. And the kind of takeaways here are also that the rise time is about 29 milliseconds and the bandwidth for the current controller is much faster, about 200 hertz, which stems from the difference in the electromechanical delays of the motor compared to the physical system. And to give you an example about how we can use the kind of sensing modalities and control, we've developed a closed loop torque controller using the load cell that's in the bottom of the design. So you can kind of see it there sticking out. And my student Ungi is kind of interacting with the system with a Ritz cracker. Here it's following a zero torque reference, and it's really just rejecting the transmission friction and dynamics. And you can see that it actually does a pretty good job. One of the things I'm proud about is the kind of website that we've developed to disseminate this project, and I just kind of want to highlight that for a minute. The project's website is opensourceleg.com, and it has everything someone would need to develop their own system. There's solid model files, a bill of materials with vendor information, design drawings, detailed assembly instructions, detailed control instructions and tutorials, an open data set for analysis. So it really contains kind of everything that people would need. To give you a little bit of an idea of what it looks like kind of testing in our research laboratory, here we have our open source leg, you have the subject wearing it during walking, and it's being run by a kind of a $20 Raspberry Pi. So that's what we're calling the high level controller in this case. We've developed a set of open source Python-based APIs that I'll talk about, I guess, in a minute. But it allows researchers to very quickly get up and running without having to do some of the low-level communication or low-level control that can be pretty time-consuming. I'm also very excited to say that the idea for this project was to become a platform for the research community that helps with study and control strategies and ultimately benefiting the lives of people with disabilities. And we currently have 8 research groups that are using the open source leg kind of around the country and around the world. So it's very exciting for us. I'm going to conclude by just telling you a little bit about the lessons learned. Kind of one of the main challenges I think that we had was that we wanted to design with belt drive transmissions for the reasons I stated earlier, but there's actually very little kind of rigorous information available. The only information we could find is about tooth skipping, and we didn't really find anything about kind of belt delamination. So as an example, we're looking at kind of input torques for the knee and the ankle for the various belt drive stages. And we used the kind of tooth skipping information to kind of predict how close we were kind of to that threshold, where the dashed line here represents our expected tooth skipping torque, and the different lines represent different locomotion activities. So we used this to kind of size the width of the different transmission stages. And then when people began to use it, we saw, I think, mostly due to kind of, I think, heel contact or strikes with the ground, we would see a belt delaminate. And that would cause the system to have to be repaired, sort of opened and reassembled. And that's been kind of a challenge, is that we couldn't find this information. And we've had to do a redesign on that. And we might have to do one more to make the belt a little bit wider. Another challenge is that we designed the system around a set of commercially available batteries that we found from a company called Vertical Partners West. And then about a year into the project, they discontinued that battery. And then no one else had a battery of a similar form factor. And this was a huge bummer for us, because now we had no longer could fit the battery we wanted into the ankle and into the knee. And what we did was we had to do a kind of a redesign of the housing. And we also had to reduce the number of cells from 9 cells to 8 cells, because we couldn't find something that could fit in the kind of form factor we needed. And in hindsight, I wish I kind of had checked into that battery maybe a little bit more and known that the market for batteries is actually a little bit more volatile than I was expecting. For control, one thing I'd like to highlight is the success that we had. So I mentioned the Python-based APIs, but we use a kind of a single embedded system from a company called Defy that really does low-level control and commutation, sensing and acquisition, and power management for us. So all we do is communicate with it over Python via USB, and it responds with the information that we need. And this, I think, took a huge burden off our team. And that product is called a Defy actuator package from a company called Defy. It's worth looking into if you're kind of interested in building these types of scalable robots. A practical thing that I kind of wanted to end on is that something I've been really amazed with is the engagement from the community and the general public. So people have contacted me from all over the world, both researchers and just general public, to help with the project. And this is just an example I received. It's an email from last year where some students at the University of Wisconsin-Madison heard about the project and reached out to me. They noticed that there wasn't sort of a gazebo simulation model, and they wanted to help build it. So they contacted me, and we set up a few meetings, and that kind of sort of crowdsourced development in academia, I think, is actually really exciting. And I think as we move to maybe more open designs and fostering collaboration amongst the community, I think we can really take advantage of this. So I just wanted to highlight that for a moment. Okay, so I wanted to end a little bit early in case there's any time. I had 15 minutes, so if there's a minute or two for questions, that's great. If we need to move on, I can check the chat. But thank you very much for listening.
Yeah, I think Elliott, thanks for the great talk. I think open source projects really can create a high impact, right? I think sounds like it's not very novel, but I can really see a lot of high impact from the broader community, not only in our smaller research community, from general public population. Yeah. So there are 2 questions from the chat box. Maybe you can answer offline because due to the time limit. And yeah, thank you.
That's great.
Let's move to the next speaker.